Hi, in this video I'm going to talk about Bitcoins. This is going to be a first one in a series. When you think about Bitcoins initially, at least this was for me, I used to think that Bitcoins were kind of like a dollar bill that has a serial number on each of them. So that somehow I thought inside the system there would be individual objects for each Bitcoin which has some kind of unique number. So when you're handing over Bitcoins to somebody else, you're handing over some tokens essentially with some number. But that's actually nothing like how Bitcoins works. To understand how actually Bitcoin works, we have to start by looking at the concept of money transactions using Bitcoins. So I'm going to start out with this example where we have Alice that wants to send 3 of her 4 Bitcoins to Bob, like this. In a transaction, what we're interested in is proving somehow that Bob now owns Alice's Bitcoins. Because, anyone can just copy some information. And if you could do that willy-nilly, then it would be possible for someone to just take your money very easily. So we need some way of proving it. And involved in that is what we call the Bitcoin wallet. So Alice's wallet contains multiple things. It contains a public key. A public key is just a piece of information that you can see below here. It's a base 64 encoding of a number that represents the public key. And this is often also referred to as an address. More accurately, the address is actually a hashing of the public key. So the address is what you give to other people that you want to send money to your wallet. Whereas the private key is a large number that we're having base 64 encoded here that you can use to send you the money you have to somebody else. So that's what allows spending of money. Just to get across the idea that a wallet is really just 2 numbers. A wallet can in principle contain multiple public and private key pairs. And I'm going to explain to you shortly why that is. But this is the most basic case. A wallet can just be a piece of paper like you see here. And you can see we have this square with black and white dots, which represent a QR code, which you could scan with a cell phone or a camera or something else to get that number that you see below into the computer. So this is a method that's used when you're a lot of the Bitcoin applications that let you do payments. It will scan the address of somebody else as represented by a QR code. In the lower right corner, you can see a so-called paper wallet printer. People make these, so they can use, say, a Raspberry Pi or some other little computer that's not connected to the internet that prints these wallets. And this is the thing that you got to understand. There's no central Bitcoin service that you connect to where you get these numbers. These are just generated kind of randomly with an algorithm, and that creates a valid wallet. Now it's not going to have any money on it, but you can give that address that you created to somebody else and they can then send you money. And the benefit of using these paper wallets is that there's no way a hacker can hack into a paper wallet. There's no internet connection to a piece of paper. So as long as your private key stays on paper, there's no access for someone on the internet to it. Of course, if you want to spend that money, you have to get that private key onto some computer system. Now let's look at how a transaction works. So this is the transaction for sending 3 or 4 Bitcoins to Bob. First thing we need is Bob's public key. This is how Bob is able to receive the money. And we need Alice's private key, which is needed for spending money. And we need some reference to a previous transaction. These are the transactions where the money came from. We're going to see how that works later. And we have an output where we specify where the individual Bitcoins go. And you can see we're spending all the Bitcoins here. And some of them are going back. That looks a bit weird. Why are Bitcoins going back to Alice? Well, the reason is because you have to spend all the Bitcoins in one transaction. So all of this information is concatenated and then hashed, and that produces a digest. So if you saw my previous video on cryptography, you would recognize what I'm talking about here. And this digest, together with Alice's private key, is fed into an encryption algorithm, which gives us the signature for this whole transaction. And that is essentially the verification by Alice that Bob now owns these 3 coins. Because anybody else can then use Alice's public key and verify that she has indeed signed this one and that it's going to Bob. Let's look at the data structure that represents the transaction. The first part is the inputs, which are references to previous transactions. There can be any number of inputs, and because a transaction can have multiple outputs, the inputs have to have an index that refer to which output of the previous transaction we are referring to. If you remember from the previous slide, Alice had to sign the transaction and provide the public key to Bob. So that means that if this transaction that you're seeing right here, if this is one of Bob's transactions to somebody else, then Bob has to provide a signature using his private key that proves that he has a private key for the corresponding public key that Alice sent the money to. So that is a proof that he can actually use these inputs. Anybody else who's going to verify this transaction will look at the transaction data structure, check the inputs, and check the signatures, whether actually the signature allows you to spend the inputs from the previous transaction. So whether this money was actually sent to you. Okay, to not confuse you, we're going to now pretend that we're dealing with the same transaction that I showed you earlier, and the outputs are to Bob primarily, and then the change goes back to Alice. So you can have multiple outputs, as I mentioned. So we're giving each of them a number or an index that can allow the next transaction to refer back to these in its inputs. And the outputs, they list the public keys or the addresses where the money is going to. These outputs can then, of course, be inputs to some future transaction, and the person that's going to create this transaction has to prove that he or she can spend these outputs by having the corresponding private key to the public key that was provided in the output. So if we put together all these transactions and combine them, you can see that it forms a transaction graph. This is an acyclic graph. The blue nodes here are the transaction objects, and the ones that are marked in orange are the inputs and outputs to different transactions. The number I affixed on each edge in the red boxes or the orange boxes is the number of bitcoins that are flowing through that edge. The number of bitcoins flowing into a node always has to be equal to the number of bitcoins flowing out. So bitcoins never accumulate at a node. So if we look at T1 and T2, we got a total of 4 bitcoins going into T3, which means that a total of 4 bitcoins need to leave as well. And likewise for transaction 4 and 3. So 5 plus 2 bitcoins goes into transaction T6, and then of course 7 has to go out. Let's look at this a little bit more in detail. I've colored all the edges because, of course, for each output, they're going to some public key. So if we say that each unique public key has a particular color, this is how we can reason about what the actual your balance is on your wallet, because the balance isn't stored in one single location. So let's look at how this works. If we start with transaction T1, it sends money to somebody with the green public key. And because it hasn't been spent yet, it's just an open output, it's not an input to any other transaction. That means that whoever has the green public key now has a balance of 3 bitcoins. And let's add another transaction. This is going to the orange one. So the person owning the orange Bitcoin address has a balance of 1. Now let's change this up a little bit and add a couple of more transactions. Now adding T3, we spent some of the green bitcoins, and now the balance is down to 2. Whereas you can see that pink has a balance of 2 and dark green has a balance of 5. And we can continue with this. Now you can see that there is a total of 2 unspent outputs to the light green a public key. So the balance in there is 2 plus 7, which is total of 9.